Good morning, Physics 20. I hope you guys are enjoying what is, for me, while I'm filming, a lovely August day. Well, today, we're doing part 2 of our lovely projectile motion. If you haven't watched the first part, which is objects thrown horizontally, go back and watch that and do the practice problems. This is objects thrown at an angle, and it's building on what it is we're doing, or what we did last day. So, once again, Nick Freya's tennis ball here. And last video, we looked at objects kind of thrown like this. So you're throwing them horizontally. So they have initial VI on the Y of 0. What is going to be different today, as we are going to be looking at objects thrown up, because I'm missing catching the ball here. So I'm like that. Okay. So notice as I am throwing the ball up in the air that you can see that the Y component of this is not simply 0. It is going up. Now, what way is gravity going? Down. So that's also going to have a play on our calculations. So we'll be talking about bringing a bunch of components of what we have done throughout the entire course so far and bringing it all together in today's lesson. So I love this particular topic. It is super cool. It just kind of culminates everything that we have done so far. So if you do have any questions with anything we have done previously, make sure you ask me those questions because we need them for this. Okay. So, ladies and gentlemen, when we're throwing objects at an angle, same basic principles as projectile motion thrown horizontally. So things like, your X and Y components. You need to break everything down into vertical and horizontal. Time is the only thing that goes back and forth. The only big difference for our purposes today is that we are going to be breaking the initial velocity into X and Y components, just like we did with our vectors that were at an angle that were not perpendicular. So essentially, we've already done all of the components of this. We're just bringing it together. Okay? Because it's thrown at an angle, all right, we need to break it into an X and Y. So what I want you guys to do is I want you guys to highlight this here. You cannot assume that your V on the vertical, your VY initial is 0. You cannot assume that. It's not going to be 0. Okay? It is going to be the Y component. You're going to have a Y component of an object thrown up at an angle. Because look, when I throw a ball upwards at an angle, it has a Y component as well as an X component. So you need to get your initial velocity on the Y as the Y component, and your Vx initial is going to be the X component of that initial speed. Okay? All right. So, and your horizontal velocity is that X component. So big star beside this section, put a sticky there, and that is the big difference. It's essentially one extra step to what we've done previously. Plus, we also have some things with time to consider. All right. So before we start with our math, let us think about our vectors. Hey guys, we're back. Sorry, we got cut off. Yay, technology. It's grand. All right, so what we're going to do, ladies and gentlemen, before we begin our calculations, is we are going to start looking at the vectors of this type of motion. Okay, so as we did previously, ladies and gentlemen, we're going to use our red arrow for velocity on the X. We are going to use our blue arrow for velocity on the Y, and we are going to use our pale blue arrow to represent our acceleration. So let's start with the easiest one first. Let's do our velocity on the X. Now remember, think back to our Vx in our previous video. Is that uniform or accelerated motion? Uniform. Very good. So because the x portion of the motion is uniform, these arrows are all going to be same size. So these red arrows, your Vx, the horizontal component of that velocity, is going to be constant. It's going to be the same size because we are not taking into account air resistance. That's beyond the curriculum of Physics 20. So we now need to look at the Vy. So when we are taking our object and we are throwing it like this, okay, notice there is a y component. Okay, the x component, the ball is going on the x, but it's also going upwards on the y, which gives us this dual arc-like motion. Now, the thing is that on the y, we are going up, but the ball, gravity, what direction is gravity going? Down. The ball is being pulled down by gravity as it is going up. Notice as I drop it on the mouse pad, I'm going to break this darn Chromebook. That's right. So when you toss the ball back and forth, notice that it is slowing down as it gets towards the top. So with our initial velocities, this would be your VIY, okay, this very initial speed there. Well, then the arrow is going to get smaller because we're reducing the speed. The speed is getting less. Now notice in the very peak of the motion of the ball, it has that very split second where at its peak, the velocity on the y up here is going to be 0 meters per second. Okay? Okay. So the next thing that we are going to need to concern ourselves with here is this piece. Now, when we're at this point, when these guys are at an equal height, what is this value here? I'm going to call this VF on the y. What is that going to be? Negative VIY. So because we are not taking into account air resistance, they're going to have the same magnitude of their velocity, the same speed as this guy, but its direction is going to be opposite. Okay, so these values here, the 0 at the peak and VFY right here at the same height is going to be equal to negative VIY. Okay, so those are some important topics to keep in mind here. And we're going to be bringing those into our calculations. Now let's think about our acceleration due to gravity. Now, is their acceleration changing? No, it isn't. So if we're going to draw a vector arrow for our acceleration on each of these diagrams here, you're going to want to draw them to be about the same size because the acceleration due to gravity is not changing. Alrighty-o? Alrighty-o. I know this stuff is really tricky, guys. I know it's pretty overwhelming, but you're doing good. Okay, so moving on to our calculations. This one's going to take a while, okay? So make sure you have some tea or something while you're doing this. This is a long question. Okay, so an object is thrown into the air with a velocity of 20 meters per second at an angle of 30 degrees. Okay, what is the total time that the object is in the air? And how far does the object travel horizontally? Okay, so let's draw this. There's the ground. Now, when the object is going to be thrown into the air, it's going to have a trajectory like this. What we need to calculate is we need to calculate this value here for distance, and we need to calculate the time. Okay, so that's what our goal is. So the distance and the time. Now, we do not here have this value. We don't have the height. So that's not going to help us. So we can't really label that. Okay. But what we do know is, I'm going to switch to blue here, is that this initial velocity here is at a 30-degree angle. Okay. So let us look at breaking down our vectors, because remember, our first step is the initial velocity of the ball being thrown up this way. It is 20 meters per second at an angle. There is an x and a y component to that velocity, and we need that before we can start going on to our vertical and horizontal. So I am going to make a triangle. This is my initial velocity triangle. Okay. My initial velocity or speed, it might be called either, is at 20 meters per second here. That angle is 30 degrees. We need to get the VIY and the VX. I am not writing a VIX because it's not going to be changing. The VX is going to be the same throughout. So like we did last time, I'm actually going to change colors here, and I'm going to keep things consistent for you guys. Last time, I think we did the blue on the Y, so VIY, and then we did pink on the X. Okay. So let's do our trig in order to solve for our VX's and our VY. So let's start with VX for no other reason than it's the color I've got. And we are going to solve for this. Well, we need to use trig to do this. And we are going to be solving for this. We have the hypotenuse, and we're trying to find this, and we've got the angle. Well, this is adjacent to the 30, so we're going to use cosine. And as a reminder, ladies and gentlemen, you don't have to memorize the sine, cosine, tangent. That is all there under the trigonometry and geometry section on your data sheet. So the Vx, ladies and gentlemen, is our cosine theta is equal to adjacent over hypotenuse. And we are trying to solve for the adjacent. So our cosine of theta is going to equal, and it's Vx over your 20, and theta is 30. Okay, so we're going to rearrange this by multiplying both sides by 20, and we are going to get 20 times cosine of 30 is going to give me my Vx. And once you plunk that value into your calculator, making sure you're in degrees, you're going to get the lovely value of 17.3205 ... meters per second. And you're going to keep all those digits. We're going to use them like we did in the last problems. No rounding until the very end. Now we're going to do the Vy. Now it's VIY or VYI, it doesn't matter. Okay. So we are now not going to be using cosine, we're going to be using sine. We're trying to find this guy. It's opposite to 30, and here is our hypotenuse of 20. So your sine of theta is equal to your opposite over hypotenuse, and your sine of 30 is going to equal your VIY divided by your hypotenuse of 20. Once you rearrange it by multiplying by both sides, you're going to have 20 sine of 30 degrees is going to equal your VIY. And so the value of your VIY is, once you plonk that all appropriately into your calculator, you are going to get 10.0 meters per second. Okay? All right. So as we did in the last problem, because one of the last big questions, we kind of boxed it off. I'm going to do that again, just so that way I have my trig kind of set off to the side like that. And it keeps it nice and neat by chunking your page. Okay. So the first thing we need to do is we need to determine the total time we're in the air. Now, remember with projectile motion, we gotta separate stuff into the vertical and the horizontal. You absolutely gotta do that. So let us break up our page into our two columns of our vertical and our horizontal. Now I'm going to be consistent because we're doing the colors here, I'm going to use, oopsie, I'm going to go back to using the blue for my vertical. Okay, so remember which is Y. Remembering vertical is accelerated. Okay, you are even welcome to write that down when you're organizing your page. And our horizontal, which is the X, which is going to be uniform. Uniform motion. Okie dokie? Okay. Let's start taking what we have and putting it into the appropriate locations. So our Vx is going to go here. That is the 17.3205 ... meters per second. Okay, so that's on our X. Our Y is going to be our VIY. Now, once again, VIY is our 10 meters per second. Now, we know we're going to need to find time, but at this point, we don't know where we're going to be finding time. Let's go, because we haven't got all our other variables yet. So just keep it in mind, time could be in either place. Well, we also been asked, how far does the object travel horizontally? Well, that means we definitely do not have the value of D, but we can write that down here because that's what we're trying to find. Let's see what else we have. Okay, we've already dealt with an angle of 30. We've already dealt with a 20. There's nothing else for us there. And we already have our data here. Okay, but guys, we're missing numbers. What do we do? We got nothing else. Or do we? We absolutely do have enough values. Let's go back and look at this Y. Now, what is a value that we can absolutely put here that we know is going to be affecting this accelerated motion? Gravity. Okay, so our acceleration is 9.81 meters per second squared. Now, this is what is going to be important here. Notice this. We have, 1 second, I just gotta pause the video. All right, I'm back. So we have our acceleration. Now what we need to consider now is we need to think about our directions, and we need to think about our directions carefully. We have yet to take that into account at this point in this question. Now remember, our VIY from our diagram earlier is going up. Gravity is going down. So if we scroll back up to our page here, well, look at this. Our VIY is up and our acceleration is down. What is that going to tell us about our signs? We need to make one positive and one negative. Trust me on this one. If you forget to make something negative, you're probably going to wind up like square rooting a negative somewhere else, because a negative and a negative aren't going to cancel somewhere along the line. So don't get that mixed up there. I am going to actively choose to make my acceleration negative. Okay, by making my acceleration negative, that means I've got up as positive and down as negative for my direction on the vertical. Okie dokie? Okay. Well, we're still missing something. We are still missing a third variable. I've given you a hint to it earlier. VF. I have hinted to you how you can find VF. There are two different ways in which you can find VF. I'm going to show you the math for both of them and some of the pitfalls that you are going to come across in the problems and things you need to watch for with this. Okay. The first one is you can choose to make the VF for your calculation here. Okay, and that would be the case of VF equaling 0 meters per second. Now, the problem with this, look at this. That's halfway through the motion. This here is going to be time half. It's going to be half of time. Okay, I'm going to actually rewrite that. This time isn't going to equal half. It is going to be t half. Okay? We want t total. So if you choose to use VF equals 0, that is where the half point is with time. So you need to take that into consideration. You are going to have to double your time once you get it. Okay? Our other option is making this VF as negative VI. Because remember earlier how we mentioned that when they're at the same point on that arc, just directly opposite to each other, when you discount air resistance, they're going to be the same same speed, different direction. Okay? I am going to show you both ways. I would recommend writing them both down. And then when it comes to calculation, you just pick which one you want. It doesn't matter. But you just need to be very, very conscious that sometimes, like I know there's one question on your, I believe it's either your assignment or your test, I can't remember, hint, where I give you something like I ask you for maximum height and maximum horizontal distance. So I'm cornering you into making you do something with that time. If you choose the VF, well, use VF as 0, well, you have to double. And if you choose VF equals negative VI, you have to divide by 2. So watch that. Be careful. Watch out for that trap. Okay. So I'm going to go 2 different routes. I'm going to label this as VF equals 0 for this half. And then over here, I'm going to go, my VI is going to, my VF is going to equal negative 10 meters per second. And that should have my units. Okay, so there's 2 different ways of going about this, and I'll show you both. Okay. So we're trying to find time because remember, time is the only entity that can jump between one and the other. So you've got VF, VI, A, and we're trying to find T. Well, what equation? This guy. So your acceleration is equal to VF minus VI over T. Well, we're trying to find T, so we're going to switch those places. Okay, rearrange this guy. Okay, I need to scroll down to keep writing. Okay, so I'm going to put my numbers in. Now, VF, okay, is 0 minus my VI, which is 10, divided by my negative 9.81 meters per second. Now, I didn't do this one earlier, so I'm just going to have to plunk this in here. Okay. So you're going to get, now remember, this is time half. Your time half is 1.019 ... seconds. Okay. Now, because it's time half and you have been asked to calculate the total horizontal distance, you need to multiply that time by 2. So our regular time is going to be, our full time, 2.03873.5 ... seconds. That is the time that you can move over to this guy, okay? As we had to multiply that guy by 2, all right? That's one method. There's this guy here. Now, the thing is, it's going to be the exact same equation. Okay, I'm not going to rewrite it out. I'm just going to use this guy here. Same equation, except the difference is our VF now is going to be negative 10. So negative 10 minus 10 divided by negative 9.81. So what happens there, ladies and gentlemen? Well, guess what we get? The same thing. 2.03873 ... seconds. Exact same value, guys. So it doesn't matter which one you use, but you just need to be very, very conscious of what is happening with that time. Watch out for it, because I absolutely have laid a trap out there with a question like this involving time, where I'm either forcing you to multiply by 2 for one part or forcing you to divide by 2 for another, depending on which part you pick. Watch for it, okay? Less than subtle hint. All right. So because I asked what is the total time, I want sig, digs, and units with this. Time is scalar, so therefore you do not need to worry about your direction, because time is no direction. Okay. Well, I want 3 sig digs for this question, so that means I'm going to go 1, 2, 3, and then I'm going to come look at these 4th and the 5th ones here. The 7 will round that 8 up to a 9. That 9 will round that up to a 4. So 2.04 seconds. So that is going to be your answer to A. Okay? All right. So we now can move over to B here, where I'm asking you to calculate the total horizontal distance. So the total horizontal distance, I'm going to take this time here and bring that up. So do not use the rounded time. No rounded time. Use the full time. Okay? We get lots of time for this question. So 2.03875 ... seconds. Use the full number in your calculations. Well, now we're going to look at our total horizontal distance. So Vx, well, this is uniform motion, and this equation is only used in uniform motion. So that means, well, we're trying to find the horizontal distance, so we multiply by time. Okay, so Vx times t, we are going to get our 17.3205. Scroll back and find that whole number in your calculator. Okay, and 2.03875. And multiply those two values together, ladies and gentlemen, and you are going to get 35.3119 ... meters. Sig digs. Now remember, I said how far. Okay, I said horizontal distance. I wanted a scalar quantity, so that means I don't need a direction. So what that tells me is then I can take this and I can round this, no direction. And all right, well, 35. Okay, 0.3. There's my 3 sig digs. Well, I've got these ones here. This one, it's not going to do anything there. That one's not going to do anything there. So we have 35.3 meters. Okay. There you go, ladies and gentlemen. That is how to do that question. I love this type of projectile motion. It's really fun. It's really cool. All right. So, ladies and gentlemen, you want to take a screenshot if you want. Okay. And then you've got that. Now what I need you to do is I need you to do some of these practice problems before you do your assignment question. Thank you. And then because as well, guys, once again, this is August. I have no idea what's happening when we get back to school. So that means if we have a test, you're going to see one like this in written response on your test. And you have one on your assignment. So, ladies and gentlemen, do these practice problems first. So then that way you're not going to have as pain and suffering involved with your test. Okay? Okay. So do those. And that is all she wrote for this lesson. I hope that you guys have a good rest of your day. No fires, injuries, or explosions. We will see you guys next time. Bye.